Hello. Can you hear me?
Can you hear me?
Is my background noise quite bad, or is it
Uh,
manageable?
Ask you, are you okay with mashed potato instead?
Sure.
Okay, no, sorry.
Yeah.
I said say first time you did the talking now.
Oh,
Yeah,
okay.
sorry.
Yeah. All right.
Without the talking seems fine.
All right. Which one is this?
Oh, this one's
the,
yeah, this one.
the MCQ steps.
Oh yeah, the MCQ that you told me, right? So I'm just putting them in. And 2, 4, 5, 10.
Thanks for organizing
Okay.
everything.
No problem. For 2, 4, 5, 10, very happy to answer. Yeah, those are good questions, but I want to focus on what you did and what you cannot lah. So I'll copy it later. Yeah, well, that's what I'm trying to say. Right? I'll copy it later.
Let's start off with the MCQs.
Sure thing. MCQ is easier lah. I suppose I can ask you directly what's the problem. So you tell me what's the problem here.
Which of the following statements is false on 37?
Okay, wait. Because audio, as in I'm gonna wear my headset, so easier for you. So wait. Can you hear me?
Yep.
Okay, I can hear you just slightly better. So I think today that will hopefully help, right? Okay. So you're saying that you're not sure which one is false. Can I just confirm that you know what photoelectric thing is? Just to say.
The photoelectric effect.
Yeah, you're okay with that first?
They fire the electrons against the gold. Is that the one?
That would be wrong. That would be wrong. Yeah, so the name photoelectric, right? Okay, so photoelectric, photoelectron is just normal electrons, and the electrons are flying out, not flying in.
Okay.
It's flying out of, in this case, what in this question?
It's like
I'm sorry, not clear. Sorry. Flying out of?
Ultraviolet radiation.
No. Okay. So again, back to the question first. Let's say you do not know what photoelectric emission is, right? Yeah, back then I have that impression also, but the question is a little bit helpful. So he say, ultraviolet radiation is incident. When you look at the adjective incident, oh goodness me, that's just a very rare. So incident means input or output lah. Let's just put it that way lah. What do you think?
The electrons are being output onto the.
And then the input will be if the electrons are being outputted, then the ultraviolet radiation, which is not an electron, right? Is a photon. Is input or output or totally something else?
Oh, I don't think it's related.
It is totally related. It is totally.
No, is it okay? So what I understand is that the ultraviolet radiation hits the zinc metal, and then the electrons leave because of the photoelectric effect.
Yeah, which means UV is input. The
UV
photoelectrons flying out is output. But the reason why that's important is because photoelectron don't just fly around, don't just if it flies around, must have some input, right? So when we talk about UV as input and photoelectron, which is just electron, okay, as output, again, photon doesn't convert into electron. That does not happen. That's not what we learned, and the physics is not like that one also. So when we say input, actually, what do we mean by input? It's not a photon, but the blah 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 of the photon. The what of the photon?
The what?
The energy. The energy of the photon, UV, absorbed by the metal, and somehow that energy is converted to the convert as the energy of the electron, which comes out as flying, something like that.
You say it's like a reaction thing.
It's not a reaction, but it's also not very complicated. They did bother to explain it. I can explain it again, but the point is this is energy input, energy output. That is, I think, a very good way to see photoelectric. So that it's not mystical, it's not magic, and it is very easy to understand because it is. Okay. Now one last thing first. Sir. Energy input, don't know how, still question mark. Energy output, then my question is, whatever you know, yeah? Is this the same or not?
No.
Okay, then what is it? It is?
It's less.
It's less?
Is less than input.
All right, and you'll be correct, and this is not because of wasted energy. This is not because of wasted energy. Don't discuss the wasted energy. Of course, there will be wasted energy. It's not because of that.
Because the other things that are
and because the input energy is split to two, one to do something inside, and one to do, well, to fly the electron out of metal. So something happens inside. So the consumption is 2 steps. What is the step inside here? That if we know, that will be the end of our discussion. No? This is the question mark. No? So what actually happened inside, you know or not? Okay. Very simple. Whenever they introduce electron in physics, not in chemistry, they always draw this one. So you tell me what this is.
Oh, the energy level.
Yes.
Level.
And the electron sitting in the metal. Yes. Come on. Yes.
To bring the electrons from one level to another, giving it energy.
That's your number one. No? And then your number 2 is what? Your number 2 is the remaining
also, the energy is used to bring it up to the next, to excite it.
No, not just excited. He brings it up all the way up. Because if you don't do that, the electrons don't fly. You want the electron to fly now, right? So
go past,
you go past. Let's just say, and then the remaining energy they just use to fly, if that makes sense,
What's the terminology?
Right now the terminology, So now the terminology, right? So then now it makes sense. This work function, let's just put it to you, That's 1 or 2. Work function of the zinc metal. Even the phrase is very revealing. I know. As in, I'm bringing it very simply to you. 1 and 2. The work function. I mean, work is joule. So the joule. You see here. The joule, the kinetic joule, the frequency will also end up being joule. HF, correct or not? HF, correct, right? So the frequency of radiation, which one are he talking about? Input 1 or 2? Okay, input, right? Great. That's input, right? Input. Then the maximum kinetic energy of the electron is talking about input 1 or 2. The electron flying away is only here, Only here you evaluate the electron as having kinetic energy. Can we say that that's number 2 Number 2, yeah? So the work function of the zinc metal is a very fancy new phrase. Hey, the only possibility is number one. The work function of the zinc metal. This happens inside the metal, The electron is the electron of the metal being, excited to the fullest. They call it ionized, ionizing and then flying out. Number 1, work function. Will this make sense based on what you know? Because I know you know all this.
That's the term.
I'm sorry, that's what?
Ionized is the official term.
Ionized is the official term for exciting until way up there.
Yeah.
When it is not way up there, you just say excite.
Okay. So past the highest level.
Yep.
Excitement is ionization.
It's ionization already. So this electron is being ionized if you have enough lah, if you have enough. If your input is not enough, you just excite and go back low.
So B is therefore true.
Okay, number 2 depends on number 1 and the input. Yeah,
so
right?
B is correct.
B is correct.
C is the answer.
Okay, the photocurrent depends on the electric. Yeah, no, it does not. There has nothing to do with the, the in R lah. In this case, no R, because the mechanism is very different, right? Okay, then let's just check D and A lah, so that you know, right? So what do you think about D and A?
I know for sure from studying.
Yeah, from studying the graphs lah, right? You are correct lah. That A is correct.
In general,
correct. Yeah, in general, that's true lah. So yeah, okay. And so as per usual, you do know a lot of things. That is important, right? Now D.
Frequency is below threshold frequency.
And what the heck is threshold frequency? What the heck is that? Just based on this diagram.
Is the minimum frequency needed to
what?
For to ionize the electron.
Yeah. Yes. So D makes sense, right? Hey, you cannot even do 1. Why talk about 2? Correct? Make sense or not? You cannot do 1. Why talk about 2? That's D. Okay?
Yep. Right.
As for revision purposes, I hope now you understand photoelectric. This is photoelectric. Very simple. We'll refer to that later on. Right? Okay. So now, 38. Why do you have problem with 38? Okay. Now, obviously, muon is not a very familiar particle to you and to me. I still do not know what a muon is. Still, I don't know. I only believe that, according to the scientists, with certain experimental evidence, muon does exist. So now I'm not gonna care. In this question, we don't care. Okay. So a particle.
But other than that,
right. So you just have to find the V, right? Because the M is there already, man. The M is there.
Yeah.
So we just have to find the velocity, the velocity of the particle. Never mind whether it's muon or not. Who cares, Yeah, who cares? Because they tell you that muon has a charge, right? Okay, so let me now ask you in terms of energy. This is the least used, your least used topic, and yet, as you can tell, it explains photoelectric emission. Just energy lah. Same thing with this one. Let me ask you. This one is, I'm going to be leading you, yeah? What energy become what energy? Think first.
The separated through potential difference of the momentum.
Momentum means there's speed lah, right? And originally there is no speed. So clearly this is kinetic energy, right?
Yeah. So
but where does the kinetic energy come from? You must always ask that one. Originally don't have kinetic energy, what?
That's true.
So what energy is being converted? Good. Now you don't say just potential, which is electric potential, okay, energy.
Is it actually?
Why is it electric? Because of charge. Hello, yes, potential difference, electric potential. So not gonna be gravitational potential. That is your lot lah as a HL physics. You do need to know that. Now, having said that, this gives you a way to do the question, right? You recognize you need to, if you want the kinetic energy, because you want the velocity, right? You want the kinetic energy, then go and find the electric potential energy. That's how you do it.
Wait. So your electric potential directly correlates to the velocity.
Because when you give him electric potential energy by accelerating it through a potential difference, like it's a very simple thing. All these fancy words, just look at it. Let's look at it. It's very simple. Look forward. A potential difference, just imagine a plate lah. I mean, that's the simplest thing lah. A parallel plate, one positive, one negative, right? This charge Q, you just help me for a while. You decide. It's okay. It's okay for you to decide. You decide it's positive or negative. Just decide.
Positive.
Okay, positive. Now, if you want this one positive, a one positive exists. Good for you, right? One negative also exists. Whichever answer you give, it's going to be fine. Now, for you to make the positive charge fly, You want to put it near the positive, near the negative, or what? For him to have a chance to fly.
Positive.
Positive, and then that's your M1, no? Yeah, that's your M1, right? That's your Q, and then I'll make a hole here, right? So that you will pass through, You'll pass through, no? Zoom. So again, what's the reason that the Q is being accelerated? Because you experience force, but that's what you expect, what, from your from your learning, I have force. I can talk about the force. I can talk about the field. I can talk about the potential difference, and I can also talk about the potential energy, right? It shouldn't surprise you that if they give you potential, they ask you for potential energy. They are very clear. They're very close to each other. I'm giving you so many hints already. I'm hoping that your knowledge is now enough. Can you do this?
Are you asking for potential energy?
Because energy change to energy, ma?
Potential or potential energy?
Is potential the same as potential energy? You must be clear first.
No.
Potential is, let's look at the unit, voltage. Voltage, right? Can you see voltage? Potential energy is very closely related to potential, as I've been saying, but it's joule, and we need the joule. We need the joule. So give me the joule, or give the question the joule. What is it? Okay, this part for now, I take it. No, it's not. It's super simple. You'll be disappointed in yourself.
Wait, the formula is in chapter 12, right?
I'm not sure about the chapter, but it's there. It's there. But I never teach you the formula because of this. Listen to me further. Listen to me for. Okay, listen to me for. You're comfortable going from field to force, force to field. Why? Because they're closely related. If you have the field, how do you give the question the force, for example?
You just give it off. When you add one thing.
Yeah, add one, only one. Either mass or charge flow, depending on what field you're talking about, right? Simple, right? If you have the force, you want to go to the field, just remove one mass or one Q. Simple, correct or not? The relationship is very close. That is why I've been impressing you. Hello, the potential and potential energy relationship is very close. They are separated by only one
charge.
One charge or one mass. Just depend on which potential are you talking about. Are you talking about the gravity potential?
No.
Then the separation is mass law. If you talk about the electric potential, then the separation is Q law. You understand me? Just like force and field. Okay? So if you want potential energy and you have potential, electric potential, and you have the charge also, therefore, the electric potential energy will be?
So it can't be B or D because it's over Q. You multiply by Q.
No, it's Q times V. It's QV, it's QV. It's QV. Yeah, it's QV.
No, the option is not B or D.
Oh, I understand what
it's not B or D because it can't be over Q.
Wonderful. So it's QV, right? It's QV, no? Right, I'm gonna write it down. So QV is in what? QV is in what unit? Is energy. So it's energy. And so Joule. And then you want to convert to KE, which does have a different formula, but you know what KE is, right? What is it?
Square.
Half mv square. But don't forget, they are both joule and they have conversion, and the conversion is 100%. Yay.
So times 2 square root. Oh, so it's 8.
Times 2 divided by m square root lah.
Yeah.
Okay. And then times m again in the outside. That's why you have the m remaining. Okay. Okay. So which one the answer is? Sorry, you're saying this one? The answer will be? Yeah, I say. Huh. Yeah. 2 times energy makes sense to you. 2 times. Like that. It's not a coincidence. Yeah? Okay. 39 is a little bit of memorization. Went through this with Ananya. In the end, I can only say to her, Ananya, You must memorize. The physicists who experiment can observe it. We cannot, so we must memorize this a bit, right? So I will just say it out to you, right? Okay. Which they don't give you. Wow. Right. Oh, this is not going to make sense to you. Oh, goodness me. Oh, goodness me. Ah, man. I'll explain in half a minute, okay? You bear with me lah. So the equation for beta decay is some guy, right? Some guy must be another guy, right? So this is guy number 1, guy number 2 lah, plus the beta. Okay, Ken? Beta. And this is a decay, it's a radioactive event, right? Decay, which means some mass is lost. There's a mass defect. Okay? The mass defect becomes your energy lah, E equals to mc squared lah, right? Correct. So if you calculate this is your mass original and this is your mass final. You will have a very small amount of mass loss, mass unaccounted for when you never mind. Look. When they MO minus MF, when they calculate the energy of this guy E1, they calculate the energy of this guy E2, and then they suddenly realize that the mass defect is much greater than E1 plus E2. There is E3 loss somehow. You don't get your energy. It's gone somehow. Okay, that's the neutrino. There's the neutrino, and which is unfortunately extremely difficult to observe. Unfortunately, so that's your neutrino. Now that is supposed to be the answer, the simplest answer, and then they give you A, B, C, D, which does not seem to relate at all. Okay. Right. So first of all, A is wrong. Why? Because every decay is like that one. Does this make sense? Every decay is random and spontaneous. That's it lah. That's not the reason to suspect there's a neutrino, because other decay don't have neutrino. Oh, this is already too long, right? Okay, A is wrong. Okay. B is also wrong because it doesn't matter. You're trying to account for the missing energy. Who cares if the beta is going through or not going through? It will go through lah. To be fair, it will go through lah. But that's not the point. You already calculate E2, right? Okay, and then D. Oh my goodness, there's no direct answer. Oh. So okay, for D, why is D wrong? D is wrong because every radioactive decay is like that one. When you decay, you become weaker, As you become weaker, you decay less, no? Does this make sense? This is a half-life thingy, half-life thingy, now you have 1,000 count. After your half-life, you have 500, no? You see, you become weaker, what? After another half-life, you become 250, no? But that happens in every decay, what? Not necessarily a beta decay. And A, B, and D is...
So it's not unique to beta decay, lah.
Definitely not, because every decay is like that. You learn that there's a 3 decay, right? That's how they see it back then. Yeah, there's an alpha decay, which is a decay, a beta decay, which is a decay, a gamma decay, which is a decay. Every one of them will simply decrease what? It's a decay. It's a half-life thing.
So it has to be C.
You're left to be C, and C doesn't make sense to you at all because they don't cover it in your syllabus. That is related. Actually, I disagree with Sila, but that was the clue. Oh, goodness me. They refer to the clue. Look. Let's just be done with C. I'll just tell you why. The researchers had a clue based on C, but C is not the reason for a neutrino. The reason for a neutrino is the loss thing. Just never mind. Just never mind. Okay, so you know that A, B is... Yeah, I don't think they should. But A, B, and D wrong is your is your benefit from this question. No? That one you need to know. A, B, and B is wrong is important. So, C is just a bonus, right? Just a bonus. No. I disagree with the question. Right? No. Nonsense. Right now, 40. Do you understand the question first? Because this requires you to understand decay lah.
Yeah, it's the you need the exponential.
Sample B with. Oh goodness me! No, oh my goodness, he's doing it there. Oh, right. You're saying. Sorry, you're saying.
And the E, right? It's a formula for decay.
There is a formula. Yes.
Let me try to find it. Do you happen to know it?
Okay, never mind. Okay, I'll tell you the story. The story is already more complicated than basic decay, right? So now you have two things that decay, right? A and B, right? B decays. So how can B? You explain to me first, lah. B is decaying. If B is decaying, how can B stays the same? Even common English already doesn't make sense. Hey, I'm decaying. How can I stay the same? Makes sense? Makes sense, right? So you explain to me first, how come in this question, he say B remains the same amount? What's going on here? What magic trickery is it?
It's not radioactive.
I'm sorry, what? It's not?
It's not radioactive.
It's not real. I'm sorry, it's not the voice not clear. It's not really?
Oh, never mind. Sorry. It remains the same amount because atoms of A decay to give atoms of B.
Very good. So B lose something, right? B loses something, right? B loses something, which you can calculate very easily. But B also gains.
Decay of A is equal to decay of B.
Something like that. Something like that lah. That's the logic, lo. That's the simple thing.
The replacement.
Yeah, that's the simple thing. That's it. Whatever I decay, I gain. So what I gain is from the decay of A, right? Something like that, right? So just like that, you can figure out the answer, lo. Just like that lah. Then you want to go to the formula which kind of tells you, is there even a formula? Right? Because in the end, you look at this, you just see either the amount.
Rate of decay is dNdt, which is decay constant times amount.
Right. So does this have anything to do? This is a weird thing, right? A constant times the original amount. What is that?
You see, ABB. Right.
Let me put it another way. Is there a formula like this or not?
No.
Okay, then this is a bit suspicious, but we'll humor it a bit. We'll just humor it a bit. Oh dear. Okay, no, never mind. I'll take the lead. This time I'll take the lead because the question is not basic at all. So, now look at. So first of all, we might be tempted to say that NA equals to NB. We might be tempted. Do you know why? Because if they start off as the same, let's say 1 kilogram and then 1 kilogram, right? Also 1 kilogram, then you can immediately say, wait, this is 1 kilogram of B. I know that the decay, the decay is always greater when there's more starting material, and it's always lesser when there is less starting material. That just makes sense, right? You at least understand that part, right? Correct? So if my loss is because of 1 kg, proportional, right? Remember, that's how they say my dNB dt, my loss is proportional to, the NB lah, right? This is a very fancy way of saying, okay, 1 kilogram loss. This one also 1 kilogram. 1 kilogram will lose something, right? Will lose something, which is the gain of B. Hey, 1 kilogram, my loss will be equal to this gain. Yay, it must be D, right? And why is that wrong? You tell me. Why is that wrong?
It's not a constant. It's at any given instant of time, and if they have different decay constants, then
you're right. We have decay
constant.
constant. So even though we start with 1 kg, 1 kg, one may decay in a slower rate, one may decay in a faster rate. They are different material. What? Correct? So what you want is not that what you want. I'm sorry. So let me put it another way. If now I turn my attention to, hey, they decay in the same rate, that must be the answer lah. A decays at the same rate as B, which is actually nonsense because no material does that. There's no material which is different but have the same decay constant. But then again, let's humor that lah. Okay, they are the same. So that must be the answer, no? Instead of starting material the same, the decay rate must be the same. So the answer must be B. What do you think? No. And you're right. And the answer is C. Not because this is a pre-existing material, but C. Oh. Right now the. Oh no. Actually, it's not C. It is A. Oh no. How am I supposed to explain this to you? Actually, no. A is wrong. No, A is wrong. So I'm gonna explain why C makes sense a little bit first, and then later on we'll work out the math. Okay, this doesn't seem to be worth the trouble, but let's humor it, right? So C is a representation of but you cannot say but A is wrong. But A is also wrong. Then what to do? Never mind. Okay, so C is maybe correct because C gives us a chance that their rate is the same and their starting amount is the same. If their starting amount is the same, kind of, and their rate of decay is the same, which is not practical at all, but let's humor that, then you are right, no? The gain will be equal to the loss. It's like I combine B and C together. It's what I'm trying to say. I'm combining B and C together. I'm combining B and D. I'm combining B and D together.
Even if they start at a different rate.
Yeah. So now,
their starting rate doesn't matter what.
Yeah. So now, since we have the idea that, hey, my rate must be the same, my starting amount must be the same, then the gain and loss must be the same. Now, by doing this, you have given yourself a certain allowance, right? So let's say that the starting rate is never the same. It's never the same. This is bigger and this is smaller. However, you can compensate that by this one being smaller and this one being bigger, You can compensate, So A decays as
it has to be the same one because in your question says since atoms of A decay to give atoms of B, and at any given time B will remain the same amount. Right? No, it's asking when will sample B remain the same amount.
No. If given
you can't just have NA equals NB, and you can't just have constants are the same.
Wait, I'm sorry. Am I reading wrongly? I'm sorry. Maybe I am. Wait, let me read. Yeah. At a given instant time.
Yeah. No, it's just the answer provided that. So we are trying to find the conditions for it to remain the same.
Okay, right. So when they say remain, no, I didn't read wrongly. Okay, so let's just confirm this first. Remain the same amount means at all times it remain. That's the meaning of the verb remain, at all times, not at one time. If B remains the same at only one time, that totally doesn't make sense. Oh, you mean in this split second, B remains the same, and after that, no. Then why do you use the word remaining, so to speak? I thought remain means it remains the same amount for a prolonged period of time.
Yeah, at any given instant of time.
Yeah, at any given instant, not just one given instant of time, but at any given instant of time, sample B will remain the same. This is okay first of all.
Yeah, I see what you mean.
Right? Because the word remain, the phrasing is not nice. He start with at a given instant of time, he's actually addressing the NA and NB. He's not addressing the sample B. Sample B will remain the same mean period, a long period of time. The phrasing is not nice, I know. But can we accept that? So at every time, the gain of B will equate the loss of B at any given of time, at any given point of time. Yeah, which is to say again, backlah. If my starting material is smaller than my starting material of A is smaller than starting material of B, then I already have a disadvantage because I must match his loss. Hey, my B is bigger at the start. I'm losing more here, and I'm only giving you less because of my initial starting material, right? But I can compensate that by decaying faster lah. Yeah, larger this one. This is small, this is big, will compensate lah. As long as you know the B is lower in losing, then I can compensate you by decaying faster. So C makes sense and A does not make sense at all. B makes sense but only part of the equation. D makes sense, only part of the equation. C makes the most sense. A makes no sense at all because of what I just described.
Yeah.
Okay, so I'm not saying that C is correct. That's not what I'm saying. I'm just using elimination to show it to you. I'm not saying that C is correct. Okay?
Yeah, again, it's another
okay. MCQ law. Maybe they're allowed to do this law. It's crazy lah to me lah. It's crazy, right? It's crazy. But hopefully you learn something. Now, have you tried question 2, 4, 5? No? If not, then I want you to do it together. Then you share screen and whatever. Okay, we'll do that. Okay. Okay. Yeah. So, yeah, I'm glad that I lead the MCQ lah. That one a bit too much lah. I feel a bit too much. Okay, you share your screen. I follow you through what is it? 2, 4, 5.
Paper 2, no, paper 2, question 4.
Oh, 4, 5, 10. Go ahead.
I've done question 4, but I haven't done question 5.
Okay, but share your screen. Right, share your screen. Show me. Yes, I'm seeing it, right? So you are in the middle of 4, right? So let me just read the 4 one more time, right? Just one more time, one more time, just to make sure. Where's 4? Where's 4? Okay, there you go. Right, this thing, blah, blah, blah. Nice. Okay, you start with all this mass defect thingy. And suddenly he decided to switch for quarks, right? Okay, so you're not at the quark stage, right? Sorry, 1 and 2, 4A, 1 and 2. Okay, you okay with this? Right, a standard.
Yeah.
Okay, good.
1 I can do. Yeah.
2 is standard, very standard. Right, let's go. Right, okay, very nice. Now this one.
This one I'm not sure.
Okay, so first of all, it will be, yeah, it's just nice for sorry.
Time.
Yeah. Yeah. Oh wait, I'm forgetting something here. In general, it's okay, you know. In general, right? Like, you know, the C, the S, blah blah blah. They tell you what, and then you analyze the charge. You will know there is a weak positive. The W plus goes on just because you analyze the charge. No, simple, right? However, there's an however. No, that's actually what. No, that's fine. No, that's really fine. No, that's really fine. I'm just not sure about the direction because I don't memorize. Okay, let me check again. Let me check again the direction. Other than that, I think we got it about right. Okay, I'm gonna put it there so that I remember that OU first. I always messed up the particle who seems to go back in time one. That one I have to check.
NT must always arrow the other way.
Yes, and because I don't understand it, I keep cannot do it. Like I'm not sure whether it makes sense. I try to read it and I don't understand at all. So let me just check with that. Okay, but of course you are correct. Of course you can always memorize it that way. Of course, right? Okay, now to 5 first, right? Okay, do you need to know? Sorry, I'm sorry. You need to know one. Do you need me to tell you?
Yes. I can't find the limits.
Okay, so the normally abundant uranium is something. When he say enrich, he's referring to the current technology. When you want to use it for a nuclear reactor, you want a uranium which is not naturally abundant. So to enrich a sample of uranium doesn't mean that you convert one to the other. That's always the mistake. You just say that when you take a normal sample of uranium, you find a very small percentage of that uranium to be what you want. Only very small, very, very small. So to enrich means
like
you are able
isotope
to separate.
Of uranium.
Yeah, a certain isotope which is rare compared to the natural uranium, and you want that. That's the problem. And they are always found together. They're always mixed together. That's the whole problem. The whole problem is that you cannot just find a particular location which has the rare type of uranium. It is always mixed. So you just separate them. So enriching means separating the abundant isotope from the isotope that you want. That's all. And taking that specific isotope. For which one is isotope, you read just like this, very simple one. They have it in your slide. One is 235, one is 238. You just have to memorize, hey, which one do I like and which one is the abundant? That's all. 235 and 238. Now you go and read, but that's all you need to read because you need to memorize this a bit. It's not obvious that I want 235 or I want 238. There is no specific, they don't tell you the specific reason why this one is. So just memorize. Okay, that's what it means by enriching. Okay, not converting. It's not converting one to the other. So, yeah. How do you separate the most reliable way is to use a centrifuge. You spin it very fast. When you spin it very fast, the lighter one, the heavier one, 238, the 238 one will sink to the bottom, so to speak, and you collect the 238 from the bottom using a centrifuge, which is one of the main technological problem that the North Korea has to overcome. North Korea, Pakistan, India, back then that's history. That's history. Okay. So part 2, you understand or not? The question.
Why are they exhausted?
All right, very simple, because the uranium field, you want them to, fusion or fission. What do you want them to do? You want them to?
Fission.
You have to, this one you have to know. So we treat it as a revision. Okay, you want them to split, fission, or fusion means to unite. You want uranium to unite or to split. Split, the term is fusion or fission. Because fission you don't know, but fusion you know, so it must be fission. Now, obviously, when uranium split, it is exhausted, right? Correct, because it's gone, Once it's split, it is no longer uranium. But it doesn't mean that the rod is gone. That's a misunderstanding. When uranium split, it is no longer uranium, but the rod is still there because it simply becomes something else. The rod is the waste product lah, but the waste product is this still solid rod one. The rod doesn't crumble one. It's there. It's there. It's still there, right?
It's
It
really
just
like
don't bother. Correct. Then he say this thing which is still there, right? Makes sense, right? Are good absorbers of neutron. Why the heck are we talking about neutron right now? Why the heck?
Why?
Because in your slide, now you have to look at your slide. You have to look at how uranium is split. Uranium-238 doesn't just split. Just look at your slide. You do something to it. Yeah. Vision. After, there you go. This thing. No, this thing. Read and read the question. Yeah, this one. No. Oh, stop it. Here. Stop. The picture. Yeah, picture. Just look at it. By the way, you're wrong. You know, the 235 is the one that is desirable, not 238. It's a 235. By the way, but how do we know? I don't know. No, we memorize. I don't know what. I don't know which one. 238 is more stable. Hey, but 238 has more number. I don't know why. The one I really don't know. Actually, the graph tells you why. But that one you just memorize, okay? So look at the question. Oh goodness me, look at the question. Look at the page. Yeah, look at this page. You have to understand this page. That's your minimum. That's your minimum level. No, not this page. Not this page. The page that you were just now. Your slide. You gotta understand this slide. You gotta. You tell me what's happening here.
So neutrons go away.
There are 3 neutrons that's born. Fair, right? Fair. But notice
Oh,
that
and then
235 will be the neutrons will. The neutrons will
become 238.
I'm sorry, to become what?
Will the 235 become 238 because of the neutron?
No, that's just wrong. The 235 will split, which is clearly not a 238. How can you do that? When 235 absorb one neutron, right? Absorb one neutron, he become 236. Makes sense, right?
The remaining 235 will
become 238. That doesn't make sense. Yeah, the remaining 235 will go and absorb the other neutrons.
Yeah,
which is your chain reaction. That is your chain reaction. This is why they tell you, because this is how you make a bomb. I'm sorry, that's how you make a bomb. We're not using this for a bomb. You're using this for a nuclear reactor. The good news is it's much harder to make a bomb. It is very, I'm so sorry. Now it's no longer hard. Never mind. The point is you're learning this in not in a bomb situation, but in a nuclear reactor situation. This will happen. The neutron will chain react so that it's automatic. It's automatic. You just have a reaction which keeps running. That's the whole idea. If you don't get that, you don't get nuclear reactor. Nuclear reactor just automatically run one. Just glow. Yeah.
Have a neutron.
Yeah, you have a neutron.
The uranium.
The 235, yes.
And then it becomes 236.
Unstable, which is unstable, which then split, but gives you 3 neutrons, which is the whole idea. That's the whole idea.
Then these neutrons hit more you.
235,
then
which gives you 3 more, blah, 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 blah. Sounds good, right? Sounds good, right? Chain reaction sounds good. Sounds like a good idea until you realize this is what happened when a nuclear reactor goes wrong. This is what happened.
So it's too much.
It's too much, lo? Nah. Then he tell you, hopefully in the next slide, hopefully let's see. Did he tell you what we must do? He does not. He does not. Let's go. He does not. This one, okay. This is the drawing. Chain reaction, okay. Chain reaction again. So far so good, right? That's what he's doing, right? But does he tell you what to do? Does he tell you what to do? For some reason, he gives you two. Never mind. Okay? And he does not tell you. Okay, let's go again. Let's go down again. He does not tell you what to do. He does not tell you what to do. Why do your slides keep doing that? Can you just go down just to make sure that it is not covered? Just go down. Just go down. Let me just check. Okay, it's not here. It's not here. Oh, okay, that's it. That's it. Why am I making a big deal out of this? Because that's what the question requires you to know. What are you supposed to do to the neutron? Okay, let's go back to the question. Now you understand the chain reaction already, right? You already understand, correct? You already understand. The chain reaction is roughly what you imagine it to be, right? Now, the waste product absorbs neutron, right? Does that sound good or bad to you?
We don't want that to happen.
Let's think for a while. Let's think for a while.
The waste products are all 238.
No, it's not. It's no.
The waste product is just.
It's whatever. It's whatever. It's whatever. It's X and Y, but it's there and it will absorb the neutron without. What they mean is like this: he will absorb without giving you neutron, whereas the 235 absorb neutron, right, and give you.
So it will stop the chain reaction.
Correct. Yeah. Let's say it stops. Let's say it stops. So is that good or is that bad?
Depends on your situation.
Good. If your situation is what, then it is good.
If your chain reaction is out of control.
If your chain reaction is slow, then it is good or bad?
Bad.
So that's bad because you want more. If your chain reaction is fast, for example, in the case of so many uranium, remember uranium gets spent, right? Exhausted, but at the start, there is more uranium. When there is more uranium, there is more chain reaction or less? Just to confirm. More. And by the way, there is less waste product. The waste product is just being formed. So there is less absorbance. Correct.
So the longer it goes on, the slower.
The more absorber. So one slow down, one absorb more. As slow and slow. You get what I mean? Both are now slow and slow, but initially it's fast and nothing. Okay. Now that's already. So I'll add one more. So initially you have your own. You have your other absorber of neutron. I hope that makes sense because nobody is absorbing it, and that's bad. You have your other absorber, and then as you decrease in uranium, you have your natural absorber. You take out your artificial absorber. Let's put it that way. That is enough for you. That is good enough. That's how nuclear reactor work. That's it. Finish. Just enough for A-level. You can form your own opinion here. Okay. The phrasing slow down the chain reaction is already good. You just have to answer it. Can I leave it to you?
Do I have to present both options or can I just choose one?
No, but I'm telling you so that you have a good idea, have a good complete picture. Do you have to present it for 2 marks? I don't think so. But do you? If you do, you'll be happy with yourself. Just a bit time spent. It's more like time instead of here. Okay. Now part 3. Part 3 is a memorization. Do you know? You can just write first. Yeah. Go ahead and write this. Yeah. Just go ahead. I'm not sure about the word peak, but I'm sorry. Can I read the question again? Because the question doesn't seem to. Can I read the question one more time? The question is state and explain, which is what you're explaining. It's slowing down. The impact of this waste. Okay, you're going bigger than the question. The question only asks you about the impact of this waste product. You're talking about how to use the impact, which is of course better lah. You're better than the question. But remember that the question doesn't ask you to tell you how to use this waste product. So you only get 1 mark here because you didn't explain how absorbance slow down. I think that's what the question wants you to do. Absorbers of neutron will slow down the chain reaction. Why? I think you want to go there instead of this one just for the 2 marks. But for your own understanding, of course, that's good lah. So waste product absorbing can slow down because give a summary of what you learned just now lah, the chain reaction thing. Okay, I'm checking the time backward thing here, which I never understand. Oh, wow. Okay, wait. I've never read this before. I'm sorry, you're referring to, you're still trying?
I'm trying to find examples for advantages and disadvantages.
No, it's just logic, right? So you're using a advantage is more environmental friendly because of what?
Less pollutants.
And the pollutant that you say must be very specific. What would they be?
No greenhouse gases.
Okay, let's say. So the nuclear power produce less, less greenhouse gases because it is not combustion, right? It's not combustion, right? Then the disadvantage is also environmental. So you cannot say environmental friendly, right? So it's true that, okay, more environmental as less, but also not environment friendly because?
No.
Because the waste product is?
Radioactive.
Yeah, so it's both lah. It's a plus and minus. It's a plus and minus from the environmental point of view. So you don't have to say that lah. You don't have to say that. Just say the let's say gas, right? And that's it. That's it. This is something that you already know. That's the good thing lah. That's the good thing about it. Do I have to memorize? Just have to remember. Okay, something like that. Okay, for 2 marks that should be enough lah. Okay, you should check your answer key for better phrasing, but other than that, it's fine. Okay. If there isn't, then the knowledge is what we have, right? Which is a bit weird, I find. I find that that's not very good. But okay, okay, this is what you have right now. Okay. Okay, part 4, which I find to be weird. Never. Okay, why do you have albedo? I've never explained this topic to you. Do you know what's going on here? This is like totally different again.
Albedo is the ratio of light absorbed
compared to compared to what is received, right? Received, so input and output, right? Okay, sure. And are you comfortable with this? We talk about it the first time we meet, but we never actually do any question.
Like a very surface level on this kind of topic.
Let me explain not the albedo, but what he's talking about. Right? Okay, let me just explain, and then you try to do it, right? Try to do it. Again, going to the Jamboard, I'm copying this into the Jamboard. Page 6. Now, radiates power at what? Okay, now what is related to joule? Again, energy lah. What is related to joule? So what is it? What kind of relationship with joule?
Joules per second.
All right, joule per second. Right. Now, this is I'm just asking for your opinion and understanding. I'm not asking for the right answer lah. So why do they say the sun radiate power, meaning what? Instead of the sun radiate energy, which of course the sun radiate energy. What? I mean, what is joule over second? Why is there a preference to say that? To them lah, you can state your own preference. I'm not asking a right or wrong question. Why do they do that, you think?
I do not know.
Okay, then let's look at your power bank. Okay, power bank is the closest thing you have to a generator. So your power bank say 100 joule per second, 100 watt, which is a very high power bank. My power bank is 130 watt. Okay, 100 watt is very high, right? Most small laptop like are you using MacBook Air?
Yeah.
MacBook Air only 65 watt. So MacBook Air is 65 joule per second. So a power bank can be higher than that. Let's say 100 watt, 100 joule per second. Would you prefer your power bank to be 100 joule per second or to be in joule instead?
Say again.
One more time, ma'am. When you're buying a new power bank for your MacBook Air, would you prefer that the manufacturer just say, hey, this power bank is 100 watt, or this power bank is 10,000 joule? Which one do you prefer?
What?
Let me put it another way. Let me put it another way. You know that your MacBook Air is 65 watt. How do we know your charger is 65 watt? Okay, so 65 joule per second. Would you like your power bank to be 65 watt? Just compared to 50 watt, for example.
More the better.
I mean, if you buy a power bank to charge your MacBook and it say 50 watt, aren't you making a mistake? Do you understand?
Yeah.
Because the power bank cannot give enough to your MacBook Air. If your power bank is 100 watt, will that be a good idea for your power bank for your MacBook Air? In general, it is because it's smart enough to not give him more. Give him more, MacBook Air also explode. Plus the extra 35 watt you can use to charge your phone, for example. Okay, so far so good. So you want your power bank to be 100 watt or at least more than 65 watt. That just makes sense, correct? Then now here's the question. Do you want your power bank to be 100 joule?
What does that even mean?
100 joule. Correct. Joule is the thing that we think about, not power. 100 watt, 65 watt, 100 joule. Let me put it this way. What does it mean if your power bank is 65 watt and also 65 joule? It means something very simple. It will light up your MacBook Air for 1 second. That's it, low. Does that make sense? The capacity of power bank is 65 joule. The ability is 65 watt. So he has 65 joule, $65 in reserve. He will be able to give you $65 per second. So he'll last for 1 second. Ta-da! That's it. That's what joule means. So now if your power bank is 65 watt, which is great, which is what we want. And then your power bank is also 100 joule. Do you want that?
No.
Me too. Me neither. Me neither. Do you want your power bank to be, 65,000 joule?
Maybe.
Maybe, except that 1,000 second is less than 20 minutes. But that's better than 65 joule. My point is very simple. You want your power bank to be fast. What lah? You also want your power bank to be at least big enough lah, please lah. 20 minutes of iPad, 20 minutes of MacBook Air. Do what? Something like that. Cannot even do one question. Can ya? Can? So can we deal with it this way? If we talk about joule, we talk about how big. If we talk about watt, we talk about how fast. That's the general meaning. I hope it makes sense. Over second is always something like a velocity. So joule per second is like how fast the joule is being given to you. That means I can have a very big power bank, but it's very slow to give you, also not good lah. Also not good. That's all it's like. So watt and joule has a slightly different meaning, and that is what we need here lah. Okay? Can ya? Now the sun's joule is infinity. The sun will not finish giving you power until 2 billion years from now. That's the current estimate. 2 billion years, you and I are dead already. We don't care. Okay, but the sun gives you joule in a certain speed. The speed is 3.83 10 to the 26 joule per second. That's the speed of the sun giving you the joule. The capacity, we don't care. So just the speed. Can ya? Can? So good. Now, here's the second question before you can answer everything about this topic, right? So the sun is here, and the earth is here. There we are. We are here sitting, one person in Batam and one person in Singapore, right? Now, the sun is giving you at the speed of 3.83 10 to the power 26 joule per second. That will be the speed. It's very fast. Does everything reach Earth? Does everything reach Earth?
No.
And the reason for that is what? Just to be clear.
Albedo clouds.
No, the albedo is the final thing. So first of all, there is the sun is giving you what? Okay, the speed of this joule per second. The second issue is that not all of the sun power reaches you. That is not albedo. Albedo is number 3. After it reaches you, Earth actually reflects some back. So there's 3 situations here. The original speed, the reason why number 2 is not 100%, and then number 3 cuts it down even more because it reflects some away. He gives some back. It's like a type. You're given, you give back, something like that. But that's not number 2. I'm asking about number 2. Why all the energy of the sun doesn't reach Earth, which is actually a very good thing, by the way. It's actually a good thing that it doesn't all reach Earth. Because the Earth is small. Let me put it another way. If the Earth is closer here by half the distance, is that a good idea or not?
No, too hot.
Too hot. Very good. You have that experience. Yeah. So why again? How does physics talk? He's specifically talking about this. So what terms or what formula do we use to talk about, hey, I am in this distance lah. I am not as close as you are. Furthermore, I'm very small. Some more lah. Furthermore, I'm very small. So what do we do? There's intensity. Very good. There's intensity. So intensity is number 2 lah. This is intensity. No? The intensity that you get. The intensity that you get considering your distance from it. Correct? This is actually wrong. This is actually wrong. Please. Yeah. What is it? No, it's close. It's close. It's close. But what is it? It's close. It's close. Come on. Now, nice is power over area. What kind of area are we talking about here? You need to know this. If you don't know this, you don't understand at all. You need to know what kind of area are we talking about. You tell me right now. What area are we talking about?
Incident area of the Earth.
Nice. And usually the shape of the can I say it? Yes, I can. The shape of the incident area is usually a
circle.
It's not.
Like oval, technically, but like
I guess that is the surface area of the Earth. I guess. So what is more? So the Earth is a sphere, but you can imagine it as a circle, right? So I'll call this circle. Okay, a circle. So I'll call this circle A lah. So circle A is here, right? You have to compare this circle A. Okay, here's the thing. Here's the thing that you have to understand. You have to compare the circle A with this. Let me draw you something. With a humongous sphere, the surface area of the sphere. You have to compare this Earth circle with the humongous imaginary sphere, the surface area of that humongous imaginary sphere. You tell me why right now. If you know this, you got it. You can answer the former. If you don't know this, you don't understand. Okay.
What is orbiting the sun?
Correct. We are orbiting the sun. So what does that have anything to do with the humongous sphere? First of all, we orbit the sun in a circle, not in a sphere. In a circle. I'm talking about a sphere, a humongous imaginary sphere.
Where the power goes out to?
The power will travel along the sphere, not along the circle, along the sphere. So this 3.83 is divided into the sphere, which ever expands. This one you understand? The Earth is only a very small portion of that humongous sphere, surface area. That is what we get. Is much less than 1%. Much less. And that is what he wants you to calculate for 4 marks. If you understand that, you got it.
How do you calculate the surface area?
This one? Oh, so simple. Ta-da! So simple. Ta-da! Don't you think? I have this guy. That's the I can use the R because surface area of a sphere only depends on the R. You tell me the formula of the surface area of the sphere. If you don't remember, then at least I'll tell you.
4 pi r.
No, not cube, but square. The volume of a sphere, 4 over 3 pi r cube. I'll list it down for you because I think you need to know this. That's the volume of a cube, 4 over 3 pi r cube. But we are not concerned with the volume. You want surface area. You don't want the surface area of the Earth. You don't want. There is a reason, because the Earth is half lit, half dark. Obviously, the other half is not receiving. Obviously, surface area is 4 pi r squared. So for the humongous sphere, so which one do you use first? The volume of the surface area. Is that fine? And then you must compare it with the appropriate surface area of the Earth, which is not the full surface area. It is not.
What's the radius?
No. Okay. This yeah, correct. The what? Sorry, the radius what?
Radius
I'm sorry, this is totally fine. This is totally fine. This is already joule per second. This is going to be meter square, and intensity is definitely joule over second over meter square lah. Correct? Yeah, correct lah. You're on the right track lah. Okay, so this is the intensity lah. Now you're forgetting one thing. So this is to make the whole thing complete. This is one. You talk about one, ma? That's number one, correct? That's number one. You talk about number two, the intensity. You forget what?
Albedo.
The albedo, which is number three. But albedo is the easiest thing. Albedo is how much you reflect or how much you absorb.
Very sure.
If you're not sure, you check lah. You check. Unfortunately, this is a bit more memorization, but it's good to memorize, right? Albedo is reflect or absorb. That matters.
Absorb.
Really, albedo is absorbed? Wait, let me check. Wait.
The formula is reflected over intensity.
Reflected over what? Over total, am I correct? Reflected over
Yeah.
total, right? So albedo is reflect lah, not absorb lah.
Yeah.
Higher albedo means you reflect more. Lesser albedo means you reflect less. Does that make sense first? Does that make sense from the definition of albedo lah? Correct or not? So if your albedo is 0.31, 31% of arriving photons are reflected. So what happens to the remaining photon?
Absorb is
Absorb lah. Absorb lah.
69%.
Correct. So they just say albedo, but you probably want to use 0.69 here lah. Probably lah. Because incident is a little bit incident is a bit vague. So incident means after reflection or before reflection. Heck, I don't know. It's very vague. I'm just going to assume it's after reflection. But it's very vague. It's very vague. It's a bit annoying. So by right, you're supposed to 0.69 times that guy lo. By right lah. That's number 3 lo. And since the question is a little bit vague, we don't have the answer key. We cannot check. Who cares? Just learn the whole topic first lah.
What is the area of the
The area of the curve doesn't matter here because the area will matter when you want to calculate the joule. Here they just want intensity. Here they
power is density is power over area, right?
correct. So you already have intensity. He wants you intensity. The top part here is already intensity ma. Welcome. Watt. This is watt ma. Joule over second watt over meter square. This is already intensity. You already have intensity. If you times it with the area of the Earth, the relevant area of the Earth, it's because you want the joule usually. In other question, they will ask you for that. In this question, they don't. I'm just giving you the full picture. Ma. Do you understand that you don't need the proper area of the Earth? Not at this question, not at this question. Do you understand yes or no? Yeah, something like that. And this will say watt over meter square. Lah. The unit is important. And you can say joule over second meter square, no problem. You can also say watt over meter square. Just know that they're both the same. You won't be penalized for that. Okay, that does sound about right. Once you times the appropriate area of Earth, then you'll get the watts. And then once you determine how many seconds you're talking about, then you have the joule. Some will want that lah. Some will not.
Isn't that quite intense though?
Is that why? Sorry? I'm sorry.
Isn't that still quite intense? Like the density is very high. 100 watts per meter square.
Actually, it is intense because of this. Because we're at the tropic, so we get the direct sunlight. People at the northern part or southern part, you go to Europe, has a glancing area lah. Like we are just hit by the sun. It's intense. Okay. Furthermore, this is only half the Earth. We are receiving entropic times 2 of this. No, I'm sorry. That's what I'm saying wrongly. I'm sorry. What we talk about? No, I'm saying wrongly. We're just receiving this. It is intense, but is 935 joule per second intense or not? Actually, joule is a very small amount. How do I know? It's very simple. How many joule do you need to raise, the temperature of 1 kilogram of water? You know it from the number C lah. You know number C, the specific heat of water. What is the specific heat of water?
4.2.
Actually it's 4,200 joule. You're getting around there over kilogram. Kelvin.
200, yeah.
Kelvin. Now let's compare this number to this number. No? It's that simple. So if you have 935 joule, how many Celsius of temperature are you raising for yourself? Remember that you are mostly water. We can use this number. Look at this number and look at this number. You have the sense of intensity from there. Is this intense? Not when you compare it with this. You're a buff person, right? Are you 65 kg maybe? 70. You are a rather big fellow, isn't it? So I must 4,200 times 70 kg lah, your weight lah. Correct? In order to raise your temperature by 1 degree, in order to make you a feverish person, you need 4,200 times 70 joule, so to speak. The sun is delivering to us in the tropic almost 1,000 joule per second. Is that intense or not? You just use your subjective opinion. Intense or not?
No.
1,000 joule per second. This is around 000, right? 280. This is almost 300,000. 300. So 300K. To raise your temperature to feverish, you need 300K of 300K joule, and the sun is only roughly delivering 100K joule, so to speak. So it's, I think, reasonable. You won't be cooked by the sun. You won't. Right? And that makes your number kind of how to say? I think you should take comfort by this number. This number seems to make sense in the absence of answer key. Correct. Well, I'm not being cooked by the sun. But if I stay in the sun for too long, I might get cooked, which is around what this number will suggest. If you stay a bit too long, a few more, a lot more seconds than what you're supposed to do, you can get your heat stroke. True. The sun has the capability of heat stroking you, but not immediately in 1 second. The number seems fine. I mean, I happen to know the number. This is a very common number to know. So, but since you don't know, there's some comfort in this. Okay, can Daniel?
Yeah.
Okay, I'm pretty sure that the next paper will give you something harder than this one. So for 4 marks, right? Now, part 2. What the heck? Suddenly he asks you the temperature. What is this then? Which topic are we supposed to talk about? This is no longer just
the mixing chapters.
Remember the first chapter you asked me back then when it's structure or something, you're talking about something along the chapter. You found the Stefan Boltzmann radiation and then the curve and then everything, something like that. The black body radiation, the black body.
Oh yes, chapter 8.
Which is around where you finally talk about albedo anyway lah. Which is around there.
Yeah, it's the same chapter.
Now that chapter is probably what we need. So if you could go there and take a look lah, Should we go there and take a look?
Just fast copy.
Yes, please. Yes, please. Do you notice that you don't draw diagrams though? So will you remember next time? I hope so, yeah? I hope so. Next time, if you don't remember this, I'll ask you to draw, okay? Not here, not here, not here. Oh, they tell you here. Wait. Yeah. Parts of the nuclear reactor, they tell you here.
Yeah, I'm gonna see this.
They tell you here. Control rods are blah blah blah, are movable that already absorb neutron. Yeah, control rods. Yeah, I mean, it's a bit weird that they talk about it here, but they did talk about it. It's a bit weird. It is a bit weird. The advantage, disadvantage must be here also. How do you flip it? You don't flip, you rotate. You don't want to flip, you want to rotate.
How?
Layout. Let's go to layout one more time. Go to layout. I have no idea. I'm so sorry. You can flip it in your own viewer. I'm so sorry. You can rotate in your viewer. Right now,
Maybe it will automatically.
but you can just read it from here. Now that you know it's there, now that you know.
That's good.
Yeah. So the artificial break that I was talking about was the control rods lah. That's it lah. That's it lah.
I will memorize all this.
They even give you a nice thing. Yeah. And the 238. So just go to never mind the plutonium first. Never mind. The 238 first. The go up. Up. Yeah, down here. Up. There. Okay. Naturally occurring uranium contains less than 1% of U-35. Why do we bother? Because U-35 is what we want. No? The normal one is U-38 lah. So there you go lah. You have this lah. It's confirmed lah. How come there's uranium-238 in the fuel rod? It's not because U-35, because U-38. Enrichment doesn't actually mean you get pure 235. You just make it richer. Just make it richer. So you have a lot of U-38 in the fuel rod also, which is useless, by the way. Which is useless. It's not because U-35 changes to U-38. 238. Yeah, it's not. It's just there in the first place. Okay. So plutonium, actually he discussed plutonium-239. Okay. Wow. Okay. Let's look at the next slide. The 239. What does he want you to know? So 238 can also fission. Oh, I know why you like this lah. I guess that's what they want lah. Yes, lah. But they don't do it by capturing neutron. They don't. The U-38 captures the neutron and then it becomes 239 plutonium, and then the plutonium will decay. Never mind. That doesn't seem to be. Just know that it exists. Just know that it exists. Right? Health and safety risks, which me where the pump storage, yeah. I guess you learn all this. They're not very difficult. We talk about conduction, convection. Yeah, black body. Okay, go up a bit. Go up a bit. No, go up a bit. Let's go up. You have to revise it. Come, we don't have much time. Go up. How much? Oh yeah. Oh goodness me, it's 1.5 hours already. Let's stop here for a while. Do you want to continue or not? This is 1.5 hours already.
I don't know.
Let's
No.
try. Okay, let's try. Let's try. Okay, right now I'm free, so let's go. So, do you understand what this line means? Oh my goodness, do you understand what this line means?
I know.
If you understand, we can go lah. But if not, then let's talk about it.
Yeah.
Okay.
So this is
Okay.
Did you have like a, is there a equivalent for emitters for black body?
I'm sorry, cannot hear you. Is there a what?
Oh, wait, there's a double one. Yes, okay. Got it.
Oh, okay, all right. Okay.
Yeah, this
Is he? No. The wins is fine. The wins is just for you to find the maximum. Yeah, not what you need late in the previous question, but just know that it's there lah. Just know that it's there. Yeah, the reason is because of it. This is for astrophysics. This is not talking. Why do you want? Why do you mix astrophysics?
we're not really in astrophysics.
Fine. Finally, we're back here. Yeah, we're back here. That because the wind is more practical in astrophysics. Not right now. Not here. Right, not here. The Stefan Boltzmann law is what we need lah. Is what we need. So look at this formula for what? Just for what? This is total power radiated for something. This is E sigma A T to the power 4. The E is a constant, correct? The sigma is a constant. You already have two constants already. Okay, yeah? You have two constants, which doesn't matter. Okay, there will always be constant. Then the area of the emitter, which is for most of the time, is also constant. You can calculate it, but it will rarely change. You're talking about the Earth, for example. Yeah, the Earth total surface area seldom change, right? The Earth stays the same, so to speak. E constant, sigma constant, A constant, so to speak. So you will say something like this, okay? You'll say something like this. So in the end, the total power lost, radiated means lost by somebody, simply depends on the temperature. Simply depends on them. Of course, you will have to talk about the emissivity. Of course, you have to talk about the area, but other than that, the temperature will be the main guy. It's power 4 anyway. It's also power 4 anyway, so it's a big contributor. That's the general concept of this, because you will now apply this to the amount of energy that Earth lost. Okay. Now I have to talk about this for a bit. Yeah? It's not worth the 2 marks. It's more than, this is worth more than 2 marks. We don't care, okay? We don't care, right? Okay. Now, here's the thing. If Earth receives almost 1,000 watt per meter square, correct? If that's what the Earth receives, then after a while, Earth will be cooked. After a while. That's what you calculate from the start, right? Almost 1,000 watt per meter square. And Earth is very big somewhere. So after a while, Earth will be cooked. Now, tell me, is that correct or not? We keep kena sun, we keep kena sun. We keep kena sun. So we will be cooked. Yes or no?
Yeah.
So why are we not cooked right now? Why are why are you and I not dying here? But the sun keeps shining. What? The sun keeps shining. You know,
Greenhouse
we will be
gases.
cooked. Greenhouse gases makes it worse. Makes it
Yeah.
worse. Greenhouse gases like traps more, so we're retaining more. We are not reflecting more. You may wish that we reflect more, yeah, become colder, man. But we are retaining more. It's worse. Again, even though it's worse, why are we not cooked? Again, why are not? Why is the Earth not having a heat stroke? We have a heat stroke. The Earth is not. How come? How come this is so partial one? Because we lose heat according to the Stefan Boltzmann law. It's an expression. We also lose heat. We receive heat and we lose heat. Therefore, the Earth is not heat stroke. We do. We cannot heat stroke because our ability to lose heat is slower than the Earth, believe it or not. The Earth doesn't sweat, but he will release heat just by the virtue of total power radiated, just by that virtue. Okay, Ken? You understand what I'm saying for now?
Yes.
So now the temperature of the Earth, remember, as the Earth gets hotter, this is the amazing thing, correct? As the temperature rises, the total power radiated is also increasing. So if we get hotter, we also release more heat, which sounds like a good thing or a bad thing right now?
Not a bad thing.
Not a bad thing. If you're getting hotter and hotter, I do want to release more and more. I wish we have that ability, right? I wish human beings have that ability. For reasons we don't, and therefore we cannot heat stroke. For reasons. So this total power radiated will be proportional to the temperature. The question is what temperature? Now here's the last thing. This last thing. Show that the temperature of the Earth's surface is 253. Okay, what does this mean? What it means is this. At 253, the total power loss will be the same as the total power coming in. That's what it means. Do you understand?
Okay. I gotta go sooner.
Which means we can only continue for 3 more minutes. No, or we can just stop now. We can just stop now and continue.
We stop. There's one more on bus. There's one more tomorrow, anyways.
Correct. I'll see you tomorrow.
Yeah.
Okay.
All right. See you tomorrow.
Yeah. Bye.